I don't know, ambulance or hospitals, so stuff like that. Sorry, guys. So, uh, basically, for the fundamentals of chemistry, I'm gonna show you what you need to know before the exam, the main stuff, okay, and the stuff that you don't even, let's say, like you don't even need for the exam. So for lecture one, okay, basically, the first lecture I've may seen, it's all about covalence, like how many of the groups, the periodic table. It's not that important, but maybe I think she's going to ask some questions about it, of course. But it's not. Let's say like it's not that. It's not that hard, you know. You see, like it's basic chemistry. Okay. I don't know if you have any questions about the covalence or the groups in the periodic table. No. Can somebody tell me? Like, I think that you all already studied a little bit of fundamentals now. Do you have any questions? The first part of the lecture one. Tick tack, tick tack, tick tack.
Are we supposed to say no? No.
I mean, you can say whatever you want. You say
Nah, I think honestly this should be pretty okay.
okay, perfect. Okay,
They
yeah.
can just
Don't be shy,
comment
man.
on general, and
Be
that's it.
here between. I'm not yelling at. Okay, mostly okay. I know that sometimes I yell at you guys, but like I'm not a professor. It's fine. We're between us. It's okay. So, for the valence of the elements, we're just talking about the electrons doublets and how many non-participating electrons you can get into a chemical compound, an atom, and the latest number of actual doublets will determine which group are your elements. So you have some examples in here. So group one, you have sodium, potassium, and silver and copper. But you see, like it's not that hard to remember them. You can I don't think you're gonna get the periodic table in the exam, but I do how can I say it? Like I do remember the whole periodic table by myself, so I don't have any problem with that. But for you, if I can give you an advice to remember which group are your elements, just you have just to focus on the cation. So Na plus, K plus, Ag plus, and Cu plus or Cu plus. You have to. Okay, that's all. Group two also the group three, it was three plus the group four, the plum, and so on. That's all. There's not much more information, not more information about this. But like for the carbon now, that's all for the valences. But for the carbon, you just need to know that the carbon it has four electrons that can bound, that can do some bounds, and we're gonna talk about after the asymmetrical carbon in isomers and isomers, and I think in the further on more lecture or lab, I think it's lab 3 or 4. We're gonna see later on. Um, Let me see. Okay, this is only for the groups still on in the periodic table, and I think that's it. Now, the most important part is this: is the intra and intermolecular chemical bonds. Know that you're gonna be asked about this in the exam. So this is the most important thing. Do you have any questions still about the covalence? Because like it's not that important, I would say. Here, I mean it's basic chemistry, guys. It's nothing.
Oh no, it's okay. Thank you. I think it's just a group here.
Yeah, it's nothing at all. So here's the most important part of the first lecture, the intermolecular chemical compounds. So in the we're talking about the bonds between the atoms into one molecule itself. But intermolecular chemical bonds, it means like two different atoms from I don't know, or two different molecules bonding together. You see, intra is inner, inside the molecules itself, the bonds inside the molecule itself. The intermolecular chemical bonds are those bonds formed with another molecule, another atom. You see, so like it's external a little bit more. Okay, that's all. So let's start. You can be asked about the covalent bond. The covalent bond, more specifically, the I mean those bond between the simple organic compounds. Okay, and you have like three types. You have the simple. First of all, the simple covalent bond. It's the sigma. I would say it's sigma. Yeah, sorry, it's a delta. Simple covalent bond is named as delta, and the simple covalent bond is between the two atoms. And these two atoms, you have only one doublet of electrons. Okay, so the first simple covalent bond is called a delta. No,
It's sigma, no? Isn't that sigma, the small sigma letter?
I think delta or
No, I'm
sigma.
pretty sure that's sigma.
Sigma
I don't think that matters though.
delta or sigma. I think it's sigma also. Yeah, I still forgot. Delta, I think it's in the fatty lipids. In the last lab session, we had the sixth lab session about the fatty acids about omega. Sorry, confused between those two. Sorry, guys. Sorry. So, the first covalent bond is simple one. It's called a sigma, and it's formed only between two electrons. It's only one doublet of electrons. Okay, between two atoms. Either like mostly those atoms are homogeneous. It means that there are two similar compounds, mostly in general. Uh, for the second one is a double covalent bond. So it means between a sigma, you have two kind of bonds, the sigma and the p one. Uh, it's delta or sigma.
No, bro, that's a sigma, okay? I'm 100% sure it's a sigma.
It's a delta. It is a delta. Okay, fine. Eh, bro. Anyway, yeah. I mean, just in writing, whatever, sigma, delta, call it whatever you want, but like, okay, it's delta. Anyway, so for the double covalent bond, you have two type of bond this time. You have the p. Sorry, you have this not only the delta, but also you have the p one. What are the roles of those type? Why do you have two different types of those bonds? First of all, the sigma will determine of it which orbital is the atom into. Okay, but the P will get into stabilizing the molecule. Why? Because if you can see in here, these two atoms of carbon, they're bonding between each other. Okay, so they're completely bounded with two doublets of electrons, right? But what is the role of the p bound? The p bound will come to stabilize the let's say the molecule, because if you don't have anything stabilizing those two atoms, they can rotate on each other. Okay, so that's the main role of the p bound. All right, that's all. Now you have the third one is this triple covalent bonding. You have one sigma and two p. So you will get like three doublets of of electrons shared between two atoms. So three valence of electrons, that's such as the professor did, right? So yeah, consisting of a sigma bound and two p bounds, and those bounds are perpendicular between each other in a three-dimensional space, if you let's say. Okay, and that's all. So the three types of covalent bonds, that's all you need to know: the sigma plus p, the sigma plus 2p. That's all. And mostly like as I've told you, for the role of the p bond, what is it for, and the sigma one, and that's all. Also, now, you have seen that I've told you about the homogeneous covalent bonds, the mostly found in the simple covalent bond. So what's the main difference between homogeneous and heterogeneous? Homogeneous covalent bonds, those bonds are formed between two the same type itself, the same atom itself. Okay, but heterogeneous covalent bonds, those bonds are formed between two types of different, or like between different types of atoms or molecules. Sorry, atoms in here, they're intramolecular. Yeah. So, um, the bounds, those covalent bonds depend on this bounds depend on the polarity of the molecule. So if those covalent bonds are non-polar or polar. What's the main difference between non-polar and polar? Polar, first of all, the polarity is the difference of electronegativity of the atom. So the electronegativity, you can find it on the periodic table. I'm going to show you how to get it even, but I don't know if the professor wants us to, let's say, to calculate the electronegativity between two atoms. But the electronegativity is the measurement of the attraction of electrons between two atoms. Okay, and if it's let's say if it's different than zero, it means that it's polar. But if it's let's say if it's equal or it tends to zero, it's non-polar. Okay, I'm gonna repeat. So for the polarity is determined by the difference of electronegativity. But the electronegativity is the difference between the measurement of the attraction of the electrons between the atoms in themselves. And if this electronegativity tends to zero or is equal to zero even, then you can say that the covalent bond is non-polar. But if the electronegativity is different than zero, it means that it is polar. So you have polar covalent bonds. Okay?
In Chiemene, it's below than 0.4 is polar, and less than 0.4 it's non-polar. I think it's like that.
Polar what?
I mean, when we do the electronegativity,
Yeah.
and when we find it below than 0.4, so it's polar, and if it is less than 0.4, it's non-polar.
Yeah, that's what I'm telling you. So when it
Yeah.
tends really to zero, it's non-polar. But like it's if it's like different than zero, like more. But the professor didn't get into the measurement still. I
So
know that.
non-polar.
Yeah,
If
but
it,
I know, but like the professor didn't get into the measurements herself, let's say, because you see, like there's a march when a diagram where you have to focus where if it's more or less than 0.4 or something, it's non-polar or polar. But the professor will clarify that if it's if let's say if the polarity, so if you have a non-polar covalent, guys, okay, it's just have to tend to zero or something. Okay, so either it's equal to zero or it tends to zero. But if you have and for a polar covalent bond, okay, it has to be different than zero. But you don't have to focus on any number, either it's with 0.4 or 0.3 or whatever. The professor doesn't want to focus even, she doesn't care about this. Okay, that's all. Just have to know mainly this stuff. The tend to zero or equal to zero, non-polar. Different than zero, polar. That's all. You don't have to focus on any number or decimal or any diagram. Okay? She. That's all. Okay, guys. Are you
okay.
still? Yeah. Are you still in there? Even.
Yeah, yeah.
Yeah.
Okay. Taha, Richard.
Hello.
Hello. Hello, my friend. Okay. Perfect. I'm just saying how many are we in there. Okay. Um. So yeah. Okay. Now for the command coordinated bound. What I mean by coordinated, it means that when you have, let's say for this example, we have the chloric acid here, uh, with the hold on, methyl ammonia. Uh, I think it's in amine here. Yeah. So when you have a doublet here, you can see in this molecule, so the CH3, the metal one here. Okay, you can see like you have a non-participating electron. What will happen in a coordinated covalent coordinated bound is that this non-participating electron will be shared with the atom of of another molecule. So it's like a kind of coordination between them. So if you see this type of let's say this type of equation, when you can see you have a free doublet of electron non-participating into any bound, and it's coordinated with another atom of another molecule, you can call it a coordinated one. That's all. Easy. Okay. Let's say okay. For the other types of bound, you have also the middle one. When you have let's say a not a non-polar, when you have when you have an atom, when you have an atom like bonding with with a transitional middle, those transitional middles are found between the group 3 and the group 4 in the periodic table. Okay, and those middle bonds, they also depend on the electronegativity and polarity. With the electronegativity of the molecule of the bound, but the bound format, you can see how polar is it. So if it's like strongly polar, as the professor said, or non-polar even, or maybe ionic, who knows? You see, so for the ionic bonds, it means that you have only the ions, the ions. So like the attraction between the ions between themselves, so like opposite signs, because you know that opposites attract themselves. Okay, so the main example that I can give you is salt. So sodium chloride, and that's all in here. Okay, now for the physical characteristic of the covalent bonds, you have the distance between the distance of the bonds, so the length of the bonds itself. You have the binding energy. The binding energy, when you can find it, the binding energy is the result of the electronegativity of between the two atoms. Okay, and it is measured into kilojoule per mole or kilocalorie per mole. You have also the polarity, as we have said previously before, and I think that's all in here. So you only have like 3 characteristics. Now also the weakest bound you can find in intermolecular interaction is the hydrogen bound. The hydrogen bound is weaker than ionic bound, and the strength decreases itself when you decrease your when you go decrease, like when you go further downward into the electronegativity in the periodic table. For the melting point, it is highly abnormal. High, and those bonds are very soluble in water. For example, I don't know, maybe for um, carboxylic acids, you're gonna see it in the lab session 5, I think, or lab session 3. I still don't remember. Yeah, I think that's it for lecture 1. Do you have any problems during lecture 1? It's only about intermolecular bounds. That's all. But if you want to see further on more, I think we have like a lab session that talk about also the amino acids and the bonds that you can find in them, and that's it. We're gonna go now for the lab session 1. Okay. For lab session 1, it was only about water and acid-base balance, such as what you have seen in the first lecture in physiology also. So the water and compound contents and everything. So this just like I would say, like if the professor wanted to ask any question about water components, she would ask about the hydro compartments or anything. So where those questions like we had it in physiology before. So yeah. So the composition of intracellular fluid, extracellular fluid, like maybe. the structure of water. You're gonna be asked about the polarity, but I don't think. Yeah. Okay. I'm just trying to find what's important in those type of. Okay, the hydrogen bonds. Yes. Okay. We have seen the lecture one about the hydrogen bonds. Also focused in the last session one. So we're responsible of the hydrogen bond to talk about its characteristics. Okay, so with the weakness of this bonds. Like they're, as I've told you, they're weaker than any bound. So they're weaker than covalent bound and then ionic bound, but have a high melting point and the high and they're also very soluble in water. And let's say also they have a high boiling point also, and that's all. What is a solvent? Yeah, you need to focus on this kind of this kind of point also, but like it's not that difficult. Okay, so basically, as I've told you about the hydrogen bonds, so that they were very water soluble. It means that water as solvent, when you, let's say, when you put a salt in it, so such as sodium chloride, the sodium chloride will degrade itself into, because it's an ionic bound, and this ionic those ions in the water will turn themselves into electrolytes. Okay. I think, yeah, that's all in his point. Okay, she gave this example in here about the sodium chloride also. Um, yeah, so basically, yeah, what I forgot to say about it. Also, so those ions are electrolytes, okay, they will be bounded also with the water molecules. So it means that the water, you know that water is polar, is a polar molecule. So you have two sigma, no, two minus 2 delta for oxygen and plus delta for hydrogen. So if the sodium is a cation, it will bind itself with the oxygen, and if anion, if the chloride is an anion, it means that it will bind itself with the hydrogen because of the opposite attractions. You see, and that's all, and that's how we can get an salt that is hydrated. I mean, okay. Let's see if there's anything else. Okay, she just gave it some examples of some few ions, so electrolytes and main stuff. We can find it in the biological, let's say, biological procedures such as potential action of the neurons. Okay. I'm gonna see if there's anything else. Okay, she talked about the polarity of some molecules. So that alcohol is polar. The lipids are non-polar, insoluble in water, and the amphibatic structure of proteins, because you have non-polar polar groups in proteins. Okay, that's all. Okay, water is ionization. This is an important point. Okay, so I think we're gonna have this kind of formula in the exam. So like I don't know how she's going to ask the formulas in simple choice questions, because I've may have told you before, the questions in the exam are supposed to be 25 and 25 simple choice questions. So yeah. So for the ionization of water, you know that water will dissociate itself into hydronium. Okay, so H3O plus and hydroxyl anions, so HO minus. Okay, and let's say if you wanna get into the not the pH, the constant of equivalence, the equivalence constant of water. Okay, you'll have to get into this kind of formula. So Ke is the constant of equivalence of equilibrium of of ionization of water. So you have to put the products on this the superior of the fraction and the reactant under. So you have to multiply the concentrations of the products between themselves, and after all, the concentrations of reactants between themselves also. But here we have only one reactant, so it's water only. Okay, and we have Okay. You have to know also that the constant of equilibrium when multiplied by the concentration of water will give you the ionic product of water, so the pH2O. Okay, and when it's equal to the multiplication of the products themselves, so the hydrogen and the hydroxyls. Okay, and after all, this is how you can get to the main pH of the main pH of water. So you have the let's say, yeah, so in this diagram. Okay, so the acidity and the bases and everything, that's all. Yeah, so nothing more. And after that, she didn't give some. Okay, yeah. I think those questions you can find it also in the biochemistry group about also for the acid and bases. So the strong acidity, the weak acidity, and everything. So the strong acids are fully ionized, and the weak acids are partially ionized, and also the same thing for the bases. So the strong bases are fully also ionized. The weak bases are partially ionized also. The same stuff for the both of them. Um, yeah. Let me see if there's something. Okay. Yeah, same stuff. Also, this is the same thing. Also in biochemistry, you will need to know this. So you can see this. You have the same sentence in your textbook or textbook also in biochemistry. I think maybe either it's the practical one or the textbook one of the lectures. I don't know, but you're responsible of this. So the pKa and also for the pKb for the basis strands. Let me see if there's anything else. Okay, so the amphilytic and the photic character of any molecule. Basically, this character is found in proteins, so amino acids themselves. We have seen them in the lecture one also. So amphoteric or amphilytic character, what is it? It is the behave. And the amphoteric character is when a substance will behave as an acid in a basic environment, or how can I say it? Alky alkylic environment also, but when they be in an acidic environment, they will behave as a base. But for the amphilytic character, it means that a molecule have at the same time an acid group and a base group. So it's the main difference between those two how can I say it? Those two characters. So if the professor will ask you what's the difference between amphoteric and amphilytic, this is the answer. So the amphoteric is the difference of behaviors that a substance can get when it comes to their own environment. So as I may have told you, if it's an acidic environment, so if we're in an acidic environment, it means that the substance will behave as a base. And in contrast to that, if it's in a basic environment, so an alkylic environment, the substance will behave as an acid. So for the amphilytic, it means that the molecule or the substance itself contain at the same time a group, a basic group, and an acidic group. Okay, that's all for lab session 1. Um, lecture 2. Okay. Ah, okay. Yeah. What's the matter? I know that. I think that someone's screen recording, so I'm gonna be a little bit quicker, okay, so that we can have like a, let's say, like a review recap, less than 1 hour at least, okay. But like if you have any question, yeah, like if you have any question, we can ask them at the end, so that the person who is recording can can have a record without any break or any pauses in there. So yeah. Okay. Let's focus on the lecture 2. So the hybridization of the carbon. Here we're just talking about the hybrid orbitals, you have sp3, sp2, and I think sp1. So for sp3 for hybridization, you'll have you will have 4 orbitals for the carbon, okay, and so, it will depend also on the simple covalent bonds, so that the carbon can form. So how do you know if you have 4 hybrid orbitals? In sp3 you have s plus p plus p and plus p. So it means that you have 4 hybrid orbitals. Okay. So for the sp2 you have 1 s plus 1 p plus 1 p means that you will get 3 hybrid orbitals. Okay. So you have 2 unhybridized p orbitals and two unhybridized p orbitals and 1 sigma bound also, but it will depend clearly. But I've told you before the when you have a double covalent bound or a triple covalent bound, those bounds from delta and p will be perpendicular to each other. Why? Because the p bounds will help the molecule to not rotate on itself. Okay, and for the sp you only have 2 hybrid orbitals. And okay, so she said like they'll be the collinear hybrids. They'll have a symmetry of diagonal and everything. So yeah. Now for the organic compounds, you have 3 types of organic compounds: the saturated one, the unsaturated, or the aromatic. Okay. For the organic compounds, you'll need to know the groups of each compound itself. So the halogenated compounds, it means that the atom will bind itself to a halogen. Okay, the halogen is a group of the group of compound that you can find it at the last column of groups in the periodic table. An alcohol. Okay, so the groups the radicals are bounded to an hydroxyl group, so the OH. The phenols, where's the main difference between the alcohol and the phenol? You can see that those two are bounded to the same type of let's say of group, right? So they're bounded to a hydroxyl group. But the main difference is the radical. So the alcohol, you can see that the hydroxyl group is bounded to a simple radical, so a simple linear molecule. But the phenol is actually binded to an aromatic group, so an aromatic molecule. It means that, like a benzene, you see like those aromatic compounds that are binded to those aromatic compounds that have a cyclic shape, right? So this is a phenol. Also the amine group. So you have the radicals. The radicals are binded to an amine group, so NH2. Either they can be a linear molecule or an aromatic, so also just such as the phenol one. The carbonyl compounds. What is the main difference? So, what is the main difference between carbonyl and carboxylic one? So the carbonyl, it means that you have the carbon. The carbon will have a double, let's say a doublet of electrons between with the oxygen. So you have a double bound. But for the carboxylic one, you'll have the carbon will have 2 doublets also with 1 oxygen, but will also bind with a hydroxyl group. Okay, so the carbonyl, you can see it's binded to 1 oxygen and with the 2 doublets of electrons, so two covalent bonds. You have 2 types of carbon compounds. You have the aldehyde and the ketone. So the aldehyde is how can I say it? Like you have 1 radical, okay, and the carbon is not only binded to an oxygen, but also a hydrogen. You can see in here. The main difference between an iodine and a cation is not that it's not that different actually. So in a cation, you can see like you have 2 radicals instead of 1. So it means that instead of having a hydrogen bonded to the carbon, you can see that you have another radical. So the main difference between the aldehyde and the cation is that they are first thing first, they are bonded to the same type of group. So they are bonded to an oxygen with a double covalent bond. But the main difference is that the instead of for the aldehyde, so instead of having a hydrogen group to bind to the carbon, you will have another radical. You see? So aldehyde you have a radical with a hydrogen, cation you have a radical one with another radical binding to the carbon. That's all. Now, let's focus on another compound. So you have also the carboxylic acids. The carboxylic acids are radicals binding to a carboxylic group. So the carbon is binded to a double to an oxygen with a double covalent bonds and a hydroxyl group, as I've told you before. You can see after all, you can see. We're gonna see. Sorry, esterification after further on when you're gonna get downward a little bit more. The functional derivatives of carboxylic acids. So you have the esters. We're gonna see the esterification, how is it done, and everything. The acid aldehydes, you're not so that responsible of this actually. The amide groups, instead of let's say like instead of having a carboxylic an hydroxyl group, so the OH, in the amide they're going to be replaced by an amide, so NH2. The nitrate we have three covalent bond with nitrogen. Okay, I would say that's all. But like I won't say like you only have to focus on the esters and the amides, but the others like the let's say like not mandatory. Like I'm not sure like if she's going to ask you anything about this because like she wasn't even focusing on this. Okay. I'd say let's say that's all in here. Now we have the types of reaction that the types of reaction that can take place in the chemistry. You have the substitution, the addition, the elimination, transposition. It's easy. It's not hard even. I'm gonna go for the characteristic for chemical. The characteristics of chemical reactions. So first thing first, you have the thermodynamics. So I'm gonna see you have seen before. Sorry, in biochemistry, and I think in the there's one lab session where you have seen some stuff about thermodynamics. So and I think after the lesson about the enzymes, right? So you can see that the delta H, if it's less than 0, you can see you have an exothermic kind of reaction. What I mean by that, I mean that you will have an exogenous calorific energy that would I mean by heat. You see, so you have less absorption of heat, so you can feel the reaction is going to be hotter and everything. But when you have a delta H that is bigger than 0, it means that you have an endothermic reaction one. So it means that if you are in a lab and everything, you can feel that the reaction is kind of getting cold. What I mean by that? I mean that the reaction is actually absorbing more and more heat. You see, so the more they absorb heat, the colder reaction can get. Okay. Let's say, yeah, whatever. Okay, now we're gonna focus more on the types of chemical reactions. So the substitution. The substitution means that you're going to take like let's take a group or radical, an atom or anything, whatever is it. Okay, an atom, and we're gonna replace it by another atom. See, easy. So this is what you call it substitution. I mean, okay. Let's look at this kind of schema that our professor done. So this kind of equation. So you can see that we have taken the x. So let's say x is an atom, right? And the I don't know the Z also in this kind of compound. What I have done is only a substitution, right? So I have taken from the first compound an X and the Z from the second compound. I have to substitute them between them together, and that's how we call it a substitution. Easy, easy, squeezy lemon. Okay. They're characteristic for saturated compounds. Okay, you have some examples. Some examples in here for like some equations. You are not responsible to know the equations, of course. She doesn't care about this. But like the main goal of having those equations in your lessons is that, let's say, like how to know. I mean, those are just examples for substitution. So for you to see how can a substitution look, you see. So you have an example here. For example, we have to substitute a chloride from this compound of dichloride, and an H from the not the butan from the butan compound in here. We have taken the H. We have to substitute with the chloride. What can we get? We're gonna get a methyl chloride with chloric acid in here. You have other examples with the phenyl, the benzene group also. Also here we have the methanoic acid with I think it's ethanol. Yeah, I think it's ethanol in here. This is an esterification actually. So the esterification takes place between an carboxylic acid and an alcohol. Okay, so here we have an example of a methanoic acid and the ethanol. Okay, you can see that you have here an ester. So yeah, this is an example for substitution. Sorry, I know it's kind of boring, you guys. Yeah, but like, I'm just trying to clarify everything a little bit more. Yeah. Okay. Now for the addition, just adding but like a new bound between sorry, like and it's just adding atoms between how can I say it? Okay, you're just adding atoms between themselves and creating a new bound. See, so here you have an example example of schema between a substrate and reactant. Okay, so what I have done in here is that we have broken a p bound. Okay, so in order to create new bounds with the reactant compounds, so the result is that you have the X and the Y grouped and bounded to the carbons. Okay, so in order to have an addition, you have to break some p bounds, some sigma bounds, delta bounds, so we have seen. Yeah, that's all. So we have some examples in here. I'm gonna let you see it by yourself. They're not that hard. Don't worry. Okay. It's just for you to focus to know how to make an addition and everything. Yeah, that's all. Because as I've told you, you're not responsible to know them. It's just for you to see how can addition can be done, how can a substitution can be done, and many others. Okay. Now for the transposition. The transposition, I mean, is that you only are changing the place or the positions of a radical of a group or of an atom or anything. So just like migration. Transposition, where can you find them? Transposition is actually a type of isomerization reactions. Okay, so we're gonna see furthermore on for the isomerization later on for the stereoisomers, the enantiomers, and the diastereoisomers. I think you
Oh,
still.
yo, Chiemene. Sorry.
Yeah.
Sorry to interrupt you. I don't know if it's only me, but I think your stream is not working.
Huh?
I don't think your stream is working. Can you like open and close and open it? Okay, I don't know. Now it's working. Or maybe it was only me.
Okay. Is it okay now?
Yeah, it's good now. It's good now.
Okay, sorry. So I'm gonna repeat from where okay, I'm gonna repeat from transposition. Is it okay, Batuhan? Yeah.
Yeah, of course, as you wish.
Oh, okay. So for transposition, I was saying, you only have we are only working with one molecule, so it's not like a reaction. Okay. So in the transposition is just only the goal of migrating atoms, migrating groups. Okay. So you're just changing their positions, right? So it's not like substitution. It's kind of different. In substitution, of course, you're migrating atoms and everything, but it's like done with two or more compounds, you see? But now we're just talking about one compound itself. Okay, so for you, so the clearest example we can have is just the isomerization reactions. Okay, so we have talking about the stereoisomers, the stereoisomers, and the enantiomers. We're gonna see them later on, of course. So just to let you know that it is only about migrating, changing position of atoms in one molecule itself. Substitution, you are substituting atoms. You're substituting, changing positions between two or three or more compounds between themselves. But now here we are just talking about migrating atoms themselves into the same molecule. Okay, so and as of the yeah, so as the professor told you, this is how the isomers can be obtained with the transposition type of reaction. Okay, now for the elimination, that's kind of interesting. Okay, so it has like several types of elimination, and mostly like we're focusing on the elimination of a kind of a group, right? So you are eliminating either two or more groups or two or more items. Atoms. And let me see. Yeah, so there are intermolecular eliminations, of course. So it's down inside the molecule itself. And for the types of I say for the types of group that are removed, we have like four types of them. You have the dehydrogenation. It means that you're removing hydrogen atoms from the molecule itself. Dehalogenation means that you're removing halogens such as fluor. For example, if you need to focus on the halogens, you can see them on the periodic table. You're gonna find them. You're gonna find them. The dehydrohalogenation means that you are simultaneously removing a hydrogen atom with a halogen compound itself. The dehydration, the most popular one, you can find them. I'm going to show you later on. So dehydration means that you are removing a water compound from a molecule or from two molecules itself. Where can you find this type of dehydration? Where can you find them? You can find them in the esterification reactions. You can see. So when you're moving from the carboxylic acids, when you're moving for carboxylic acid, the OH group, so the hydroxyl group, and from the alcohol, you're removing the hydrogen from the OH. You see, so this is how we can get an esterification, and this is what we call it also a dehydration. But also, you can find the dehydration mostly in the fatty acids creation, not creation, sorry, fatty acid reactions. So it means that when you or not fatty acid, yeah, triglyceride formation, yeah. So this is the last lab session. So this is the lab 6. So you can find a dehydration in them. I'm gonna show you. Hold on. Lab 6. Yeah. So how can you form a triglyceride? You need for the reactant a glycerol and 3 fatty acids. Okay. So what will happen in here is that you're gonna get to remove the OH group from the glycerol and the H. So the H from the fatty acids. Okay. To form the bonds between between those compounds, it form the triglycerides. Okay. So when you're removing an OH and an H, it means that you're removing an H2O, right? So you're removing water. So this is why you call it a dehydration. So as I've told you, dehydration are mostly founded in esterification and the formation of triglycerides. Okay. I think maybe this kind of question you could be asked in the exam. Yeah, my own self, I would say. Okay. Where we were still on. Hold on. Okay. the exercise. Okay, this is the second part of the chemical reactions. Okay, so now we're gonna focus more on in the intermolecular bonds. So you have the condensation. Condensation means that you're, for example, you're joining two organic molecules into one to become it to let it become larger. The condensation reaction are mostly found in the metabolism, also metabolism activity. You can see, like we have talked about previously about catabolism, but for the condensation, now we're talking about the anabolism. The anabolism is the reaction where you have to involve like small molecules and condense them between together to form one large big ass molecule, right? And this type of reaction involves actually energy, so you need energy to create to condense molecule between themselves, right? And that's all. But here we have talking about for biochemistry to focus more further on. We have talking about the polycondensation. So polycondensation means that here we're focusing only for the biochemical properties, the biochemical compounds. So, for example, we have the condensation of amino acids. When you condense amino acids between themselves, you're gonna get peptides or oligopeptides. The oligopeptides, the polypeptides, etc., 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 will condense themselves between each other to form the main the largest molecules, aka the proteins, right? Say another example, we also have the condensation of monosaccharides, or we can also remain in monosaccharides, right? So the condensation of monosaccharides will get to condense the condensation into disaccharides, okay? And those disaccharides can form also the polysaccharides, right? So this is all the main idea of the condensation, where you can find them and how the procedure is, how can you do a condensation? What is the main difference between the condensation and polycondensation? And that's all. Yes, I think, yeah. And now for the polymerization. What is the main difference between condensation and polymerization? In polymerization, you're also condensing small molecules between themselves to form a larger molecule, right? But the main difference between a polycondensation and a polymerization is that in the polymerization, you are condensing and binding and linking the same types of monomers, so the same types of molecules several times. Okay, so when you're binding several monomers molecules between themselves, you are creating a large molecule. We call it a polymer. So the main difference between a polycondensation and polymerization, sorry, is the difference in the difference between the molecules. In a polymerization, we are linking between them. We are linking only the same type of molecules, so the monomers, in order to create a polymer. But in polycondensation, we are linking, we are binding, condensing two or more types of molecules, and they are different kind of, yeah. So and for the general formula of the polymerization reaction, you can see it's in here. So the M represents the monomer, and the N, the small N, you can see. Okay, it represents the number of monomers we have. Okay, so this is the general formula for a polymer. All right. Poly addition reaction, the P bond is broken from each monomer to form this delta bond. Okay, whatever. Change in the aggregation state of monomer. Okay. Here our professor talked about the methyl polymethyl methacrylate, the PMA, the compound found in dentistry for prosthesis and everything in dental aesthetics. Okay, so here she have talking about the formation of polymethyl acrylate. Okay, but you don't need that so much. Okay, I'm gonna show you what you need in PMMA in another lecture. Okay, and I would say that's all for polymerization reactions. Okay, now I should have given you also an example. As I've told you, the N represents the number of repetition of the number of succeeding monomers you have in the polymer. Okay, that's all. Okay, yeah, okay, you don't need that much. For polymerization of the metal polymetal acrylate, you only need this type of reactions. Be sure 100% that you're gonna have this type of question. I don't care, screenshot it or something, print it on your head or something. Okay, you are responsible to know the formula of the metal polymetal acrylate. Okay, this is important. She has talking about so several times. Okay, now okay, now I have the alkylation. So the alkylation is the introduction of an alkyl group to a substance or something. Okay. Okay. The acylation. Just adding an acid radicals also, so the H2O to another organic compound. Okay, let's see if there's anything else. Okay, for the example, let me see how many. Okay, for the acylation, you are responsible for of the formula of the equation. Sorry, of the aspirin. Okay, so this one you can see in here. She's going to ask you about how to form the aspirin. So we need salicylic acid and acetic group. Acetic chloride. She's going to ask us for this also, guys. Screenshot it. I don't know. Do something. Okay. Okay. Now I believe you have screenshot it all. I think 1, 2, 3. Okay. Now I'm gonna go further on more. Okay, this you don't need it. Hold on. Okay, so the oxide reduction reactions. So, for the exam, she's going to ask you about what's an oxidation, what's a reduction, what's an oxidant, what's a reducer. So the oxidation is the chemical process where we're donating electrons, and the reduction is where we're accepting, we're attending even electrons. That's all. And the oxidant is the one who will accept electrons. It means that it's the reduced one, and the reducer is the one who will give up electrons. So it means that it will proceed to it will be oxidizes. It will proceed into oxidation. Okay, and when you have an oxidation, so when you have a less number of electrons, a less number of electrons will increase the number of oxidation, and higher number of electrons. So it means when you have larger minuses groups or negative groups, okay, you have a decrease of the oxidation number. Okay, I think, yeah, let me see if there's something else. So, okay, so she has given example, not like examples, but like a schema also about the number of oxidation. Yeah, that's all in here. That's all for lectures 2. Lab session 2. Lab session 2, Shaz. You have to know everything, I would say. Sorry, guys, yeah. But like the lab session 2, she have recap it on the bounds, okay, the all types of bounds, okay. She has given you several examples, but she have focused more on some many stuffs in intermolecular bounds. I'm gonna talk about I'm gonna talk about it now. So okay. So you have the hydrogen bounds and the intermolecular bounds. Okay, I think someone left. I know it's boring, but we're just focusing on everything, guys. I'm sorry, but yeah, I'm trying my best for it to not be boring. If you have any recommendation, maybe a break or something, you can ask me. Okay, but now let's focus on. So for the intermolecular bonds, you can find the electrostatic interaction, the hydrogen bonds. It means that you're involving a hydrogen compound with another, but in electrostatic interactions, you're only involving the charges. So let's say so the charges. So the polarity of each molecule between them. Okay, this is an example where you can find the hydrogen bonds in DNA structures, the water and everything, and the amino acid structure and whatever. Okay, I'm not gonna focus so much in there. Okay, now for the protein structures, so you have them also in the biochemistry books. Sorry, but like I'm not going into this because I think you already know them. I'm sorry, guys. Yeah. Also this. Yeah. The Van der Waals. I think I'm gonna talk about this now. Okay, just in this lecture, they're all easy. Okay, the Van der Waals forces, I'm going to tell you about them more further on. So the Van der Waals forces, you have like 3 types of bound, and they're one of the weakest bound you can find them. You have the hydrogen bounds, the dipole interaction, and London dispersed forces. The hydrogen bonds are in the Van der Waals forces are considered as the strongest one. Okay, but like for the others, such as the ionic bonds and the covalent bonds, they're considered as the weakest one. But you have something like weaker than hydrogen bond. So you have the dipole interaction, the London dispersive forces, and those 3 types of bonds are called the Van der Waals forces, and they are one of the weakest bonds ever. Yeah. Yet they are the weakest also, but like they have the highest melting point as we have seen that together in the first lecture. That's all for lab session 2. Lecture 3. Let me see if there's something important in here. Okay, the isomers. Yeah. Tell me, guys, do you need a break or something? I don't know. Let me see how much of you have left. Let me. Okay. Is it okay for you guys? You have any question? Like, is it so? I don't know. Yeah. Okay. Perfect.
No, I think
You good?
yeah, I'm good.
Okay, I'm gonna continue further on more on the lecture 3. So for the isomers, okay, be sure that you're gonna have a question in the exam 100%. Okay. Um. Okay. So isomers, you have like 3 types. You have the constitutional ones. You have the configuration and the conformation. What is the main difference between those 3? We're gonna see further on more. So the constitution, it means that for the geometry, so the 3-dimensional structure of the molecule itself. So we can have like several types of isomers. For the configuration one, so the second type of isomers, we have the stereoisomers, the steric isomers, the spatial ones, and many on. The conformation, you have the conformers, and so on, so on, so on. So for the constitution isomers, the constitutional ones, it means that we are focusing on the migration, on the let's say on the arrangement of the atoms in the molecule itself. So it means that when you have like let's say like the same compound, so that you have the same not like the same number of carbons, the same number of hydrogens, the same number of, I don't know, of oxygen, everything, but like the arrangement of those atoms, the arrangement of the groups inside of these atoms will differ and will give you a different formula. This is why we call it also. This is why we call it a constitutional isomers. So it means that you have the chain isomers. For example, we have the butane and the isobutane. I don't know if she has given an example of molecule and an example of these 2 molecules. But I think you have them in your text in your notebook. Sorry, I don't have it in here. Now for the second one, you have for the constitutional isomer, you have the position isomers also. So that for example, we differ with the let's say the position of a double bound. So you have the example of 1 butane, 2 butane, okay, and so on. Okay, let me see if there's other types. Okay, we have the triple bonds, aromatic nucleus, and so on, so on. The functional groups. Okay, so so it means that you have the let's say so the difference between the molecules when it comes to the position of the groups involved into the molecules, so the organic compounds. So for example, here we have the example of an alcohol. See, so the propanol. 1 propanol and 2 propanol means that it's only the main difference between them is the position of the hydroxyl group. Okay. Also, you have here it's not an alcohol, of course, it's a chloropropane. So the main difference is the position of the chloride into the molecule. Okay, so those all are constitutional isomers, just only the structure, let's say the three-dimensional space, the three-dimensional structure of the molecule itself. So you have the chain isomers, the position isomers, and so on. That's all. Let me see if there's something else in here. Functional isomers. Okay. Now for the configuration isomers, this is the most important one. I think she's going to ask you the main difference, like maybe, for example, she's going to show you this kind of picture and to ask you, like, is it stereoisomers? Is it, I don't know, is it like an enantiomers or anything? So let's focus on the configuration isomers. It is the second types of isomers, guys. Okay, so the stereoisomers would define the orientation of the atoms in the space. Okay, so we have the confirmation isomers on here. You can see, for example, here you have dimethyl. Okay, those are dimethyls, so the A and B. Okay, but the main difference between these two is that you have a rotation of sorry, yeah. So you have a rotation of the atoms themselves. Okay, you can see between the difference between A and B. Okay, and as I've told you before, for the p bound helps the molecule to not rotate on itself. Okay, but now we don't have the p bounds. We have only a single type of bound. Okay, so you can see, like, the atoms are rotating in themselves between the atoms are rotating into the molecule itself. Okay, and now we have, we call it a stereoisomers. Okay, so this is the first type of configurational isomer. Now we have the optical isomers, the easiest one, I would say. How can you get an optical isomers and where to find them even? The optical isomers are the most popular one in biochemistry compounds. The optical isomers, we can find them in amino acids, and sugars also. So let's the exos. We're gonna see them in the last lab session. Okay. So the optical isomers, what it involve? It involve a asymmetric carbon. What is an asymmetric carbon? An asymmetric carbon is a carbon that will link itself with four different type of substitutions, so atoms or groups. Okay, it is really important that those four groups or four atoms has to be different. You cannot get the same type of hydrogen, the same type of atom, or you cannot get like two types of hydrogen or something. If you let's say, like, if those four substances are not different, okay, you cannot call it an asymmetrical carbon. Okay, so it's so important it's so important on this type of isomers for the carbon to have four different types of atoms or or groups. Okay, like, if you have the same type of compound in it or anything, it's not called anymore an asymmetrical carbon. It's so important. Okay. So you need really to focus on this type of idea, what I'm telling you right now. Okay, now for yes. So for the optical isomers, you need to see in the molecule, like, how many types of how many times you can see the asymmetrical carbon in the atom, especially when it comes to, I don't know, like polypeptides, or maybe I mean, this is harder for you guys, of course. You can get to see them in medications also, for maybe I don't know, antibiotics or something like this. You see, so there are several types of of asymmetrical carbons. Okay, so and the number of asymmetrical carbons will determine you how many stereoisomers you can get, right? So let's say, like, if you have like one asymmetric carbon, it means that n equal 1. So it means that if the 2 is the exponent 2 is exponent to 1, it means that you will have two types of stereoisomers. As an example, if you have like I don't know, it's possible to have in a molecule to have like 4 asymmetric carbons. Yes, it's possible, guys. So if you have like 4 asymmetric carbons, it means that you have 2 exponent 4. Means that you will get 2, 4, 4, 8, 16 stereoisomers. Yes. Okay. Now for the L and the D, now for the L and the D types, okay. For the amino acids, you only have the configuration the L1. It's very important to know. And for the sugars, okay, for the sugars in biochemistry, mostly, the natural types of sugars are found in the shape of the D1, okay. That's all in here. So for the optical isomers, those are called those are called enantiomers. Okay. What do you call it? What do you call it? An enantiomer. An enantiomer is when you can find a difference in the physical chemical properties of one molecule one molecule itself. So in enantiomers, you can find them only when you want to have a how can I say it, like the main difference between the two types the two types of the same molecule is that the mirror facing between them. You see, for example, the L1, so the L molecule, so the L amino acids, you can see it's reflecting as a mirror to the D amino acids. So this is why we call it an enantiomer. In an enantiomer, you have to find two things. First thing first, the asymmetrical carbon. You can see in here in the amino acids you have like four different types of bonds or substituents. Sorry. So we can find a hydrogen first of all, a carboxyl group, and an amino acid and a radical. Right? There are 4 different types. So you have found if you have found an asymmetrical carbon, you can find the you can find the enantiomer of it, right? So means that you can find the mirror facing on the molecule type. Okay, so this is how you can get an enantiomer. Let me see. Also for the stereoisomers. So the stereoisomers stereoisomers are different in the complication of number of asymmetric carbons. Let me just check in the difference. So okay, so the diastereoisomers and the main difference between the diastereoisomers and the isomers is that they're those are both stereoisomers, but the main difference is that in diastereoisomers you cannot find the object mirror projecting molecule. You see, like they are not the same, right? They're not facing. You can see like they seem. Let's say like they do not seem to face each other, because you can see for the chloride in this molecule they're facing in the same direction. So it's not like a mirror facing object or anything else, right? So it doesn't have the same effect. But you can see for the hydroxyl in here. So for the third carbon in the chain, you can see that they're different the opposite there are different opposite directions, so it's kind of mirror facing, but not 100% unfortunately. So it means that if it's not an enantiomer, it is a diastereoisomers. Diastereoisomers and enantiomers are stereoisomers, and those stereoisomers are called the optical isomers. Okay, so but the both of them have an one or more asymmetrical carbons, but the main difference between them is that if they have the role of mirror facing image or not, and only in enantiomers you can find the object mirror image relationship, but in their stereoisomers you cannot find them even. Okay, I think that's it. Now for the epimers and the anomers, characteristics of isomers the characteristical isomers that can be found in sugars only. Let me check. Okay, so basically it's just only about the rotation of the hydroxyl groups of the hydrogens or anything. And for the so yeah, uh, let's say let's focus them on the sugar chapter. Maybe it's better. Let me check it for the yeah. Not that important. Just she's only talking about the inorganic phosphate. Um, yeah. Okay, we're done with lecture 3. Lab sessions 3. Let's see. No. Okay. Lab session 3 is not mandatory. You don't need to study it. Erase it. I don't know. Lecture.
Sorry.
Yeah. I don't know. Okay, but it's the main idea of lecture 4. Yeah. Let me check on the lab session 4. Okay, for the lab session 4, for the metal methacrylate, what you need to focus is just only on this formula. That's all. That's all. I know that we have written so many steps and equations and everything, but the main idea is this only. Okay, I don't know, screenshot it or something, whatever. Okay. Yeah. So, blah 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 blah. Okay, now for the sugars, my friends. Okay, now we're focusing on the sugars. So, the classification of sugars. So the monosaccharides are the smallest monomers of you can find in sugars. Okay, they cannot be hydrolyzed, such as the amino acids. They cannot be hydrolyzed even also. So, the monosaccharides are small monomers. If you combine two, or if you link together two monomers, you can get a disaccharides. Okay, so that means that you have two monosaccharides units by why am I even saying it in Iranian? Two monosaccharides united by unit by one glycosidic bound. Okay. Oligosaccharides, it means that you have two or more type 10 monosaccharides united together, and that's all. But more than 10, you have what you call it a polysaccharides. Saccharide, sorry. Okay. Now for the types of sugar, you have the glucose, you have the starch, you have the starch, you have the glycogen, you have the cellulose. I think she have done a diagram, a schema, when she have focused on the difference of the types of the sugars. I'm going to see them all further on more. Here she has talking about for the monosaccharides, the aldose and the ketos. So the main difference between the aldose and the ketos is for the aldose, you have an aldehyde group, and for the ketos, you have a ketone group. Okay. This is the main idea. So yes, I've already said that. Okay. Now also for the classification, you have the number of carbons. So if you have one carbon, you call it a monosaccharide. Okay. So you have three carbons, triose, four carbons, tetrose, five pentose, six exose. We are going to focus on mostly on pentose and exose. So mostly we have two types of exos that are important for the exam, and one type of pentose, which is the fructose. We need it for the exam also. Okay. Yeah, for the classification. Okay. For sorry. So for the exam, you need to know the structure of the glucose and the galactose. Okay. So for those exos, you can see the main difference between them is the third carbon. So the orientation of it. So and in the exam, if she asks you about what type of isomers are, you can see in here. This is an optical isomer, and this is what we call it a diastereoisomer. Okay, so yeah, that's how you can get some questions in say fundamentals of chemistry. So what is happening in here? Okay, so yeah, you are responsible to know the structure of the glucose and the galactose. Let me say check also for the fructose now. Here, okay. Also, you're responsible of it. You're gonna see later on where you need the glucose, galactose, and fructose, because there's a chapter that, if you remember still, where we have binding glucose and glucose to form. I don't know. I don't remember even glucose and for example, glucose and fructose to form lactose. I think. or glucose and galactose for maltose and so on. There's a lab session when we have done this even. Like if you remember still on. Also this is an important idea. So for the polymerization of the monosaccharides, you need to know something is that the sugars in their natural shape is they're in their natural series. There are a D series, okay? They're in D. But for the amino acids, there are L series, okay? L natural series, okay? Um, yeah. So she has given an example, but if you still remember from the lab session we have with her our professor, she has said like maybe she's going to give you two types of compounds of glucose, and she's going to ask you what is the natural series of glucose, and what you have to say in the exam is that the D glucose is the natural series of the glucose. Okay. Yeah. Um, okay, we have talking about the isomers still. Let me check if there's something important. Okay, now for cyclization. Okay, it's going to be a little bit hard. Okay, but I believe like if you have focused a little bit in the class, it will be easier for you. If not, we're going to try to do it all together. And let me just take a screenshot. Yeah. Okay. If I still remember what we have done in the class, hold on. Okay. I still remember. So the professor have taken an hydrogen in here. Okay, and then she has given up. Okay, and so when you have given, so it's like a substitution kinda. So when you substitute a hydrogen with a link of the oxygen with the carbon, okay, what will happen is that the oxygen itself it will bind after all with the carbon, okay, to stabilize the molecule further or more, and that's how we can get this cyclization. I would say. It's easy. It's not that hard even. I don't know why we have even spend a lot of time in it. So you only when it's cyclization, you take a hydrogen, the hydrogen of the group of the last group of carbon. Uh, After you bind it to the first carbon and the I mean, you'll have to substrate. So sorry to eliminate one, let's say one link, like one bound with the carbon, and we'll have to stabilize with the hydrogen that we have removed, and that's all. I'm going to let's say, hold on, yeah, whatever. Okay, I'm going to repeat. So you only take one hydrogen from one hydrogen from the hydroxyl group that is binded to the sixth carbon. So the last, sorry, not the six. So yeah, so the last carbon on the chain you can see. You bind the oxygen after with the first carbon, and when you stabilize the oxygen of the first carbon with the hydrogen group, and that's all. Uh, I mean, yeah, that's all. Yeah. Okay. Also, I forgot to tell you also for the Piran group. So, sorry for the Piran shape. So for the cyclization. When you do your cyclization, guys, I mean, try to rotate your molecule after. Okay, so you can see when you want to get your oxygen into here, you start with when you wanna how can I say it? Okay, when you want to draw your cyclic compounds or your piran come on piran molecule, okay, of sugar, you will always start with the oxygen, right here, and after you continue with the first carbon. Okay, so when you rotate your molecule, you can see where are the positions, the exact positions of the hydrogens and the hydroxyl group. Okay, so when you rotate your come on when you rotate your oxygen, you can see the hydrogen here of the first carbon is upwards, okay, and the hydroxyl group is downward, and so on. The hydrogen group is upward, the hydroxyl group is downward. Okay, the third carbon. The hydroxyl group is upward, and the hydrogen group is downward. And so on, so on, so on. After that, you close it with the metal, with this one, okay, hydroxy metal group and the sixth carbon, and that's all. It's not hard, okay, it's easy, but you have just to focus to focus a little bit more, to concentrate yourself, to not do any let's say like any error, okay. But unfortunately, like, it's not that hard to do. Okay, the professor have to give it also some examples for the beta, so the alpha and the beta, like the alpha, the alpha D glucose. We have the OH looking downwards, and the beta one is you have the OH upward. But the general formula you can see is the alpha one. So the natural one is the alpha D glucose. Okay. Yeah, I'm just repeating what is the on the let's say on the PDF. I know, but like I've told you, I'm just focusing on the main ideas. Okay. Okay, no, this is not important. Lecture 4 is done. Let's see if there's anything else. Lecture 4 is done. Lecture 5. For lecture 5, okay, just like biochemistry, oh come on, first lecture we had with Dr. Spino. Okay, what you need to focus on is the physical chemical properties of the amino acids, and I think also the bonds that you can find in the polypeptides. Okay, and what else? What else? What else to focus on? Let me see. So yeah, so the peptides that I've told you, and that's all. It's not that big. Okay, you only focus on the physical chemical properties, the types of bonds in the peptide. So and the peptide bonds you have to focus on. You are not responsible to know the amino acids at all. Asking the professor, you are not responsible to know the shape. I mean, yeah. So you're not responsible to know the. Sorry, hold on. I have a message from. Okay. Yeah, so I was saying, you are not responsible to know the amino acids, where there are polar, hydrophobic, or anything. Nothing at all. I would take it as my responsibility to tell you that, okay? But I've asked the professor before, okay, and she has told me that, okay. Yeah, that's all. Now for lab session, let's say lab session 5. Okay, for lab session 5, um, yeah, for lactogen 5 in here, we're talking about the disaccharides. Okay, as I've told you, you are responsible to know the formula, the shape of glucose and maltose and fructose. Why? Because in order to that, you have to be able to do what we call it a dehydration of reaction to synthesize, for example, maltose. You can see it here, and the sucrose. Okay. So yeah, so this is sugar you can find in kitchen, basically. So yeah, you are responsible to know that the hydration reaction in order to synthesize either maltose or sucrose. Okay, and the glucosidic linkage 1.4 and 1.2 for fructose and glucose between them. Okay, syllabiose, no. Lactose, yes, you're responsible. Let me check if there's something else. Oh yeah, now for the polysaccharides, okay. The professor here in this PDF, she has talking about each type of polysaccharide. So the glycogen, you have there are polysaccharides that contains alpha glucose linked by alpha 1.4 and alpha 1.6 glucosidic bonds. More branched than amylopectin. For storage, so localization storage, they are stored in the liver and the muscles. Okay. Yes, you are not responsible of this. Okay, now test cellulose. There are also there are polysaccharides that contains beta glucose residues. We have seen the beta glucose in the other PDF, the previous one, 1.4. Know that us Homo sapiens or human beings, we are not very able to digest cellulose because we don't have cellulase. It's the enzyme that is responsible of I say this the come on. Yeah. So destroying the cellulose. Mostly the animals, the mammals that have cellulase is the cows, so the bovine ones. You see, the sheep and everything. Okay, so those are more that have a vegan, like a vegetarian, the vegetarian diet. Here, Professor have given you, have been given us, sorry, the a schema for each polysaccharide. For its cellulose, you have the subunits and everything, the amylose, the amylodextrin, and glycogen. Okay, you can see also the difference between the shapes. Okay, you are responsible of this also, of course. And I think that's all for this PDF. Now for last but not least, okay, the lipids. What you need to know for the lipids. Okay, so the lipids we need to know the characteristics. Okay, she's going to ask you about like the water solubility, the energy, the storage in it, and the high and those. I mean the vitamins and hormones a little bit more. She knows. Sorry, I'm not. I mean she's not going to ask you about vitamins, but like vitamins are considered also as lipids. And so vitamins are classified. Vitamins with hormones are classified with one kind of type of lipids. I think they're called minitunus. I don't know. I'm going to go further on more. So you need to know the classification of the lipids, or if they are saponifiable or unsaponifiable. What I mean by saponifiable, it means that if you can turn them into a solid or not. Okay, so it means that if they are so if they have a saturation of the or they are unsaturated fatty acids or lipids. Okay. Here you have a branch of the for the lipids. You have the simple lipids. You can find the fat, the compound lipids, the phospholipid, glucolipids, and so on in biochemistry. You have the derived lipid, the fatty acid, the alcohol, sterol, and so on. The miscellaneous lipids, as I've told you, so the vitamins and the steroids and the hormones, okay? But let me tell you that we have to focus only on the fatty acids and the simple lipids. So, for the simple lipids now, my friends. The simple lipids, the general formula of this is the CH3, CH2N, COOH, etc., etc. Okay, so it's a general formula to focus on. Now, for the types of, I mean, the features, also those fatty acids, we have two types. We have the unsaturated and the saturated fatty acids. So, for the unsaturated and saturated fatty acids, we are responsible to know the let's say the characteristic of each of this. I think the characteristics are in here. No, not in here. Okay, so for the unsaturated fatty acids, you have to focus on the omega-3, the omega-6, and the omega-9. I'm gonna show you for the general formula of those three types of omega, and what I mean by omega even. Okay, because the professor know that the professor mainly is going to ask you about the omegas. Okay, now, okay, for the difference between saturated and unsaturated fatty acids. So in the saturated fatty acids, you cannot find any double bond in it. So it's literally a virgin lipids, virgin, nothing at all. So, but in unsaturated fatty acids, you have a double bond somewhere in here. Okay, so, and I have to say something for the physical chemical properties of unsaturated fatty acids is that when you have an unsaturated lipid, it means that you have a higher degree of solubility. All right. It means that also the level of cholesterol will be decreased also, and for example, for phospholipids, glycophospholipids in the plasma membrane in cells, we can find that mostly the lipids or the fatty acids are unsaturated. Why? Because it will be, I mean, it enable for the plasma membrane to be more permeable a little bit for other main compounds and to be let's say to have this characteristic of being semi permeable means that not permeable, but like a little bit also permeable. You see, like 50-50, let's say. Okay, so as I was saying, for the unsaturated fatty acids, you can find a double bond. Okay, like two or more double bonds, whatever. Okay, but like you have like two types. You have the trans and the cis. What I mean, but what is the main difference? The trans, you can see that the hydrogens, okay, they're opposites, right? They're opposite directions. But in cis unsaturated fatty acids, you can see like those two hydrogens are they're directing in the same sense, so the same direction. Okay, so this is the main difference between trans. You can see trans means that it's different. Cis, it's like direct. So you can see like they have the same direction. All right. That's all in here. Let's see further on more. Okay. No, too many informations for nothing. Um. Okay. Now this is more. This is the most important point. Okay, we have taken let's say four types of fatty acids in here, and we're focusing them in here in this page. Okay, you are responsible to know the general formula of those fatty acids, so the etheric acid, the oleic acid, the linolenic acid, the alpha linolenic acid. What is the main difference between them? So the etheric acid, you can see in here how we have written them in here. Okay, you can see this W type of letter is called the omega. Okay, this is how you this is in Greek. Okay, this is how you write omega. All right. So let's go back to etheric acid. So you can see in here we have only 18 carbons. Okay, how do you count them? We go from the zigzag. So the first carbon is the methyl group in here. We go down. You have like a point in here. You can see one, two. Let me just maybe if I can write it for you, it's better. I think. Hold on. Okay. So okay, I'm going to write in here. So 1, 2, 3, 4, 5, 6, 7, 8. Sorry, 8, 9, 10, 11, 12, 13, 14, 15. Sorry, 16, 17, and 18. See, easy. Okay. You don't have any double bound in it, so you can put a 0 in here, or you can simply put C18. Okay. And you don't have any methyl group bounded to any let's say I don't know, like any other carbon. Now for the oleic acids, as you can see, we have only 18 carbons in here, so you count here 18, right? Now how many types of you have to put like if you have any types of bound in here or not. Okay, so here is an error, it's supposed to be 1. Okay, for the oleic acids, this is omega 9. Okay, so for omega 9 you have one type of bound, so you have to put double points here 1. This is an error, it's supposed to be 2, it's supposed to be 1, sorry. Now, what about the omega 9? When you have to put omega, first thing first, omega, we have to put it when you have a methyl group binded. Okay, so it means that you have, whenever you have a methyl group, for example, here in the carbon 9, binded to the carbon 9, you have to put omega 9. That's how you get the omega 9. And for the other example, for the linoleic acid, okay, you also have 18 carbons, right? And two types of double bonds, so unsaturated fatty acids. So it puts double point 2, comma. For the omega 6, when you have a methyl group binded to the carbon 6, you have to say it. I mean, so you have to put omega 6 in here. That's how you write the general formula in fatty acids. Okay. Let me tell you that mostly the professor is going to ask you how to write a general formula for the fatty acids. Okay, and now last but not least, the alpha linolenic acid. So the most important one for our brain to how to work and everything. Our most important lipid is the omega 3. So the alpha linolenic acids. So you have 18 carbons, such as you can see. So as the others, okay. So 18 carbons, okay. Now in here you have three types of three double bonds. You can see. So it's mostly unsaturated, so you have to put 3 in here, right? Now for the position of the methyl group, if you have a methyl group in the groups 3, okay, you call it now a omega 3. So it's like C18 double point 3 comma omega 3. So this is the general formula for omega 3. All right. That's all. Okay. Now,
Chiemene. Oh, sorry. Can I
yeah,
ask you
go.
something before?
Of course, you
You
can
know,
ask.
you said the omega is when the first carbon is CH3 and delta or whatever the other one was when the first carbon is carboxylic acid.
Yeah,
Okay, so that's okay, whatever. But like when we go to triglyceride formation, did we reach there yet?
yeah. We
Yeah.
have
Well, as you can see, they all start with a carboxylic acid. So
carboxylic.
yeah,
carbox-
no, when we're
Um,
making triglycerides, they all like
yeah,
the carboxylic acid is on the left, right?
no worries. I'm gonna tell you. I'm gonna tell you about this. But let me just finish about the
Yeah, yeah,
artist. Okay, just this page. I'm going back to the radicals. I'm gonna tell you how to do it. Okay. Now, so for you are responsible to know the characteristics and the physical properties of fat and unsaturated fat. So for the fatty acids. So if they have a higher melting point or a lower melting point. So for the saturated fatties, okay, know that when you have saturated fatty acids, they have the ability to be like to have a higher let's say like they are stronger. Okay, when they are stronger, it means that they will link together like so strongly. See, so it means that they will those bonds and they are like kind of unbreakable. Those how to break those bonds, those strong bonds, you have to melt them in a high point. Okay, so that's why we say that they have a higher melting point, first thing first. And in a room temperature, so in room temperature, in standard temperature of 25 degrees Celsius, they are solid. They cannot be hydrogenated because they are saturated, so they don't have any double bonds in there, and they have a high cholesterol content. For firstly, in contrast of this, we have the unsaturated fatty acids. They are more breakable. They're more easier to break because of the double bonds found in them. All right. So the melting point will be at the lower, and they will be liquid. So just like the oil, you can see for these saturated fatty acids, we're talking about butter. Okay, so the solid fatty, the fatty lipids or shea butter also is also in cosmetics also. Yeah, they can be hydrogenated because of the double bonds that can be found. And as I've told you, for unsaturated fatty acids, you can find them in the plasma membrane, and and if you have an increase of unsaturated fatty acids, it means that the cholesterol will not have a space for itself to be in there. So it means that you cannot find cholesterol. So no cholesterol content in unsaturated fatty acids. Now for a question, Batuhan. So for the triglyceride formation, you'll be asked about this also in the exam. You have asked me for the fatty acids. So for why is it started with carbon? Sorry, the carboxyl group, right? You can see here we have a radical, right? The R prime, the R2 prime, and the R3 prime. So the R radical is an abbreviation to tell you that you have other carbons. You see, so it's only an abbreviation of the number of carbons. You can have like 17 carbon, let's say in here, because or I don't know, 15 or anything else. You see, because like the fatty acids are so long, they're big hydrophobic long chains. You understand, about Duhan or?
I get it. I get it. That was a dumb question.
So this is the radical. The radicals is just an abbreviation of the fatty acids because it's so long. See, so you cannot put it in the in your equation actually because they're so big. For example, we have seen for the omega 6 and 9 and 3 that there are formed of 18 carbons. Okay, so when it comes to the formation of triglyceride, basically you don't have time even to put them to literally put them in the equation. You see, you don't have in the sorry, you don't have time in the exam, right? So instead of working so hard, we are working smarter, right? So instead of we're writing the whole equation, the whole formula of the fatty acid, you just have to abrade it with the radical. Okay. Now, for as I've told you, the triglyceride formation is kind of an esterification. No, not necessarily. The triglyceride formation is a type of dehydration, as I've told you in the first lecture. So, the triglyceride, how to form it? You will need a molecule of glycerol and 3 fatty acids, right? So, in order to form the triglyceride, we'll have to dehydrate and condense both compounds. So, first thing first, you'll take an OH, the hydroxyl group of each hydroxyl. Sorry. So each hydroxyl group of the glycerol, okay, and from the 3 fatty acids, we'll take the hydrogen. Okay, all right. Now, now that you have dehydrated the molecules together, you will get to condense them, okay, like to bind them. So this oxygen can see in here, this one, this biggest one, oxygen you can see, okay, it will bind directly to glycerol directly, okay, here, you see, easy. So in order to form, I will repeat, in order to form triglycerides, what we'll need is to dehydrate it, to do the dehydration reaction type. So I take hydroxy group from glycerol, alright, and the hydrogen from the fatty acids. And once I will get rid from the water, okay, I will condense each fatty acid to the glycerol, all right? I will link them together and condense them in order to form a triglyceride. Now you have a triglyceride plus 3 molecules of water. That's all. So the arachidonic acid is non-mandatory. It's about pain, prostaglandins, and everything. So how you feel pain, how it works, and everything, how your sympathetic system works, and everything, blah blah blah. You don't need it for the exam. She doesn't care. Okay, fuck it. That's all. Do you have any question?
No.
Okay. That's all for fundamentals of chemistry. You have done everything.
Amazing.
Everything is done. That's all. Finish. Finito. Stop showing. How many are we in here? I know that we have left. I know that sometimes